If carbon built the molecular foundations of the modern world, polymers gave those molecules scale, strength, and versatility. From packaging and clothing to electronics and medical devices, polymers quietly reshaped how civilization builds, moves, protects, and heals itself, often without people realizing how revolutionary they truly are. This is the Learning Studio, where chemistry is explained not as isolated reactions, but as the systems that shape everyday life. And after understanding how organic chemistry unlocked carbon's versatility, the next step is to see how linking carbon-based molecules into long chains transformed society at an industrial scale. Most people think plastics and polymers are just cheap synthetic materials, but in reality, they are engineered molecular systems. For example, the softness of rubber, the strength of nylon, the flexibility of polyethylene, and the transparency of plastic bottles all come from how repeating molecular units are connected, arranged, and allowed to move. These properties are not accidental, they are designed. At the molecular level, polymers are made when small molecules called monomers link together into long chains. The length of the chain, the way chains branch, and how they interact with each other determine whether a polymer becomes rigid, flexible, elastic, or tough. By controlling these factors, chemists can tailor materials for specific purposes, from lightweight packaging to high-strength aerospace components. This understanding was fundamentally shaped by Hermann Staudinger, who challenged the belief that plastics were merely loose clusters of small molecules. He proved that polymers are long-chain macromolecules, a concept that laid the foundation for modern polymer science. His work transformed plastics from curiosities into predictable, designable materials. Once polymer structure was understood, innovation accelerated rapidly. Synthetic fibers replaced natural textiles, plastics replaced metals and glass in many applications, and new materials emerged that were lighter, cheaper, and more adaptable. Polymers made mass production easier, reduced costs, and enabled technologies that would have been impractical using traditional materials alone. Polymers also revolutionized medicine. Disposable syringes, sterile packaging, prosthetics, contact lenses, and controlled drug delivery systems all depend on polymer chemistry. These materials can be engineered to be flexible, biocompatible, or biodegradable, showing how molecular design directly impacts human health. At the same time, the widespread use of plastics revealed new challenges. Durability, once seen as a strength, became an environmental problem when polymers accumulated as waste. This pushed chemistry into a new phase, one focused on recycling, biodegradable polymers, and sustainable material design, showing that chemistry must evolve alongside its consequences. And once we understand how polymers reshape materials, industry, and daily life, the next question naturally follows. If chemistry can engineer plastics and fibers, then how does it design metals, semiconductors, and advanced materials that power modern technology? That question takes us directly into the next episode, where we explore materials chemistry, from steel to semiconductors.